Assalamualaikum and a very good evening everyone. So today we're going to continue with our lecture on designing memory system for the microprocessor 68K. So before we move on to this topic, let's recap what we have learned so far last week. Basically last week you have looked at what types of memory is available to be interfaced with the 68K. We have many types of memory, ROM, and then we have RAM. Okay, and what's the difference between ROM and RAM? And then we have look at why do we need address decoder system, and lastly we have looked at how we're going to design an address decoder system. Basically we have two types of address decoder. We have full address decoder and we have partial address decoder. So I believe on the full address decoder side I already covered this. So basically the steps of designing the full address decoder started with first determining the address range for each of the component, your peripheral, your memory. Okay, you got to identify what's the base address, the size of memory that you're going to connect to your 68K, and lastly the end address. Okay, so basically if you have your base address and your size, then you can calculate the end address. And then for the second step is for you to determine the address line that will be linked to memory and to decoder. So you have looked at on designing a full address decoder. Okay, first we're going to start with the base address and you're going to find out with the end address here. Okay, your base address, your end address, and then you're going to look at what changes in the bit. So I believe I have covered this. So if you can't remember this, you just have to look at my previous recording, and all of the bits, okay, all of the address lines that changes from 0 to 1, we denote it as X. So the X part here, okay, all of this will be connected to the address bus. Your final E0 here, again this connected to UDS and LDS. And then for a full address decoder, you're going to use the remaining address bit to be connected to your decoder. So in this case, the most easiest decoder we can think of is using a NAND gate. So this is on the full address decoder. So today we're going to look at on how to design a decoder using the partial address decoder scheme. So the concept is fairly the same, okay, the steps are fairly the same, but there is a bit of difference in which we are going to use external decoder chip here, 74LS139 or 74LS138, in order to connect the 68K to the peripheral that we want to connect. Okay, so there's an intermediary between this peripheral and the 68K. Either we want to use 7LS138 or 7LS139. So I believe let's look at the easiest way for us to understand is just to directly to look at the question or type of question that will be given. Okay, so basically the steps are the same. Again, determine your base address, determine the size of the memory you wanna interface with your 68K, and lastly calculate the end address. And then for every chip, so this is the what differs between partial address decoder and full address decoder. For every chip, you determine the total address line directly to go to the memory. Okay, this is the part which is still the same. Okay, you need to find the total address line at the chip, and the lower address line, your UDS, LDS. Okay, oh sorry, this is not UDS and LDS. The lower address line directly go to the memory. Okay, first total address is calculated from this equation. Okay, and then you need to identify similarly like the table I shown you last week. Okay, you need to figure out which part directly goes to the memory and which part can be leveraged to use as a decoder. So it is fairly the same, and this is what meant by the lower address lines. From the lower address go to the memory, and then lastly, based on the balanced address line total device, we're going to use decoder to activate one device at a time. So this is the steps required for you to use a partial address decoder scheme. Okay, so now without further ado, let's look at how we're going to design an example on how we're going to design a partial address decoder. So this is just an example of a question. Yeah? The question asks you to design a partial address decoder in order to make a microprocessor able to communicate to each of the device below. Okay, so you have your 68K. Okay, your 68K. You want to communicate the 68K with all of these devices listed over here. So first you have your ROM chip. Okay, base address is given, size is given. Then you have your RAM chip. Again, base address is given, size of the memory is given, and lastly you have an I/O chip, input output chip. Similarly, you have your base address and then you have your end address. So because I/O chip is not a memory, so when we want to specify a location for I/O, we directly specify the beginning of a address and the end of address, so there's no size over here. Okay, so if you calculate from 800000 to 80001F, there's a total of 32 address being allocated for this I/O chip. So we want to design a partial address decoder to be interfaced with all. We want to design a partial address decoder that decodes the addresses bytes so that it can connect the 68K with all of this peripheral over here. So how are we going to do that? So the steps are fairly the same. First, you got to identify the base address and end address. So here you have, for your ROM chip, the base address is at 0000, the size is 32 kilobyte. Again, using your calculator, you can determine that what is the end address. Okay, so for some of you that don't know how to calculate, okay, so I'll be going very fast over here. So how are we going to calculate this? A minute. So how are we going to calculate this? Again, it's fairly easy, not so complicated. You have your base address as 00000, sorry, 000000. So 60. Okay, it's 00000000. Okay, this is hex, and then this will be add on with the size of your memory that is allocated. Okay, that the size of the ROM chip that you are using. So for our ROM, we are using 16 kilowatt, equivalent to 32 kilobyte. So 32 kilobyte, 1 kilobyte is 1024. Again, you multiply with 1024, you get sorry. Again, let's see, in hex is 000000. Okay, and then plus with 1024 times 32, you'll get, which equivalent in hex is 08000, and then finally you got to minus this by 1, so you'll get 7FFF. Okay, so this is your end address for your ROM chip. So start with 00000, ends at 007FFF. So remember that is for your ROM chip. And then we're going to calculate for our RAM chip. Start address is 40000, size is 128 kilobytes. 64 kilowatt is equivalent to 128 kilobyte. So 128 kilobyte. So make sure you have that size in hex. Okay. So do your calculation in your calculator, and then minus by 1, you will get your end address is 41FFFF. And the IO is the same thing. Okay, it's already given. Your IO is being allocated at this address 800000 to 80001F. So you can imagine that in your memory address, starting from, okay, let's use a different color for different peripheral. So let's use green. From your 00000 up to the, sorry, which part? Up to 007FFF, up to this part here, 007FFF. This memory address will be allocated to your ROM. Okay, so in the next part, your RAM part, starting from 40000 to 41FFF. Okay, this will be allocated to your RAM. RAM. Let me erase this for a while. Why can't this be erased? Not sure. Why can't this be erased? Okay. Just, I'm not sure why I can't erase that, but let's move on before wasting any time. So imagine this is your RAM, yeah? The red part here is your RAM. Okay. And finally, your address 80000 up to the address, so this is a bit smaller, final address 80001F. This will be connected to your input output peripheral. Okay, so you want to design a system in such a way, in the memory addressing scheme, it is like this. From this address is connected to ROM, this address connected to RAM, and this address connected to the IO. So once you figure out the starting and the end address, what you're going to do is the same way, is the same method that you're going to determine in a full address decoder. You're going to figure out which part. Why can't I remove this? I'm not sure why can't I remove this. Why can't I remove this? So hold on for a while. Okay, sorry for the hiccup just now. So basically, so once you have figured out what's the base and end address, so similar to your previous steps in designing the full address decoder, you're going to determine which bit changes, okay, which bit changes in this address memory. So the one that it changes, we're going to connect it directly to the address bus, whereas the balance address, the balance of the upper address will be connected to your decoder. Okay, so for example, in the first case here, for your ROM, we have determined that the base address here is 0000 up to 007FF. So basically 000000 is all 0 up to 007FFF. So you can imagine that from 0000 to 7FFF. So here you have, if written in binary format, this part is 0000, this part is also 0000. 7 means that this part is, so what is 7? 7FFF 0111. Okay, this FFF, then everything else is 111111 1111. So you can imagine that the one that changes from 0 to 1, this part over here, all of that part you're going to denote it by X. Yeah, X. So the unchanged part is this part over here. Okay, this part over here is unchanged. Okay, so the one that changes, you're going to connect it to the address bus, and the one that doesn't change, you're going to connect it to the address decoder. But there's a bit of difference on how you're going to connect it to your address decoder between the partial address decoder scheme and the full address decoder scheme. So you do that for your RAM and your I/O as well. Okay, you'll end up having a table like this. Okay, so here from now on, we are going to design a partial address decoder. So by the name itself, we're not going to use the balance of the full address. We are going to use a part of the address to connect it to your address decoder. So in a partial address decoder scheme, we want to use a little address line, as few as possible, as little as possible. Okay, so how are we going to do that? So you need to check, okay, in this address pin between the ROM, the RAM and the I/O, what changes, how many numbers of pin from the address line can be used to select between the ROM, the RAM and the I/O. So in this case over here is clearly obvious. We have 3 devices, so we need at least 2 bits. Okay, 2 bits that can change, at least 2 bits, because you know that with the total of 2 bits you can have up to 4 different combination. Okay, 00, 01, 10 and 00. So we need only 3, hence we need to use at least 2 bits. So here we identify that this part over here, address line A22 to A23, can be used to select between these devices. So only 2 pin is required, A22 and A23. So here is these steps. Okay, choose minimum address line to select one of the 3 devices, hence we use A22 to A23. Okay, how about if the question, if you have, let's say, 5 devices, so you can select from here to here. Okay, because 5 devices, 2 bits, you can have a maximum number of 4 devices, whereas if you have 3 bits, you can have a maximum number of 8 devices. So if you have only 5 devices, you use 3 bits over here. Okay, so now we have identified the number of address that we can use is 2 bits, which is A23 and A23. So how are we going to design our, so what is the next step? What do we need to do to design the partial address decoder? So in a partial address decoder scheme, sorry, there's a glitch in my computer. So in a partial address decoder scheme, instead of designing a gate that selects between your peripheral, we use an intermediary chip such as the 74LS139 address decoder or the 74LS138 address decoder. So 74LS139 basically is a 2-bit address decoder. You have 2 inputs, hence the number of output you can have is 4. So if you look at this data sheet, they have this truth table which you can check. Okay, where is this? So this one. So the truth table, sorry, there's a glitch on my computer, I'm not sure why. So for 74LS139, you see, depending on the AB over here, the input AB, you have a different output, Y0, Y1, and Y2 and Y3s. For example, if both input A22 and A23 is low, then all of the output of the 74LS139, the output of the 74LS139, Y0 will be low and the rest will be high. Okay, so that is when both are low. So what if one is low and then one is high? What if your A23 is low and A22 is high? A23 is low and A22 is high. So you have your output to be Y0 to high, Y1 to low, and Y2 and Y3 to high. So that is during high and low. Okay, so during A is high, B is low, you have high, low, high, high. So that's how it works. And then again, just another example, what if it changes? Okay, what if when the B is high? So now what B is at? B is 1 and A is 0. So you have an output of high, high, low, high. And then when the last one, when both are high, 1, 1, yeah? When both are high, you have an output of high, 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 and finally low. So you can imagine that depending on the bit over here, depending on the input bit, okay, your output bit you will select which output bit to be low. Okay, which output bit to be low. So why do we need low? So again, if you can recap back, okay, to select a peripheral, chip select over here, chip select, sorry, there's a glitch again, chip select over here, you need this to be low. Okay, you need that to be low. Chip select over here, you need that to be low. So and then once you come up with the design, sorry, so once you come up with the design, wait a moment. So once you come up with the design, the overall mapping of between your 68K to the peripheral will look like this. like this. So that's how you design a partial address decoder. So this is the input. Depending on the state of the input, you have your decoder selects between your ROM or your RAM or your I/O. So, and each of these is connected to different address in your memory address space. Okay, so this is how you design the partial address decoder. Okay, apart from 74LS138 139, you have 74LS138 which can be used. So just now 74LS139, you can only select up to a maximum 4 devices. So how about if you have many devices you want to connect with your 68K? So you can use 74LS138, which consists of 3 input. So 3 input, and because you have 3 input, you have a maximum number of 8 output you can use. Okay, 8 output you can use. So this is example on how you're going to design a system with 74LS138. Same question, you have ROM, RAM and I/O. So this is example. Okay, how we're going to use. If you check the data sheet of 74LS138, okay, it's a glitch over, I'm not sure why. I'm not sure why is this glitch at the moment. So for 74LS138, okay, you see, instead of having 2 input with 4 output, we have now a 3 input with a maximum number of 8 output. So depending on the states you are connecting your device to, okay, for example, in this case you see A, B, C, the input is A, B and C. I'll just give an example. If all is 0, if all is 0, 0, 0, means that the output of only Y0 will be low, 0, and the rest will be high. Okay, so it selects the first input, the first output. What if it's 1, 0, 0? Let's change this to another color a bit. For example, what if it's this 1, 0, 0? So when it's 1, 0, 0, 1, 0, 0, you have your second output to be low, okay, and the rest is high. So only the second output will be low, and so on and so on, and so on and so on, okay, and so on and so on. So you can imagine if it's 0, 1, 0, change this to another color for clarity. 0, 1, 0, you'll be selecting your output pin number 2. So 0, 0, sorry, so it's not 0, so it'll be like 1, 1, 0, 1, and so on. So it's according to the truth table. You can use this as well for the question. You can use 74LS138. It's up to your preference, okay, but in general, if you have you've required only 3 peripheral, that's the best way. Then it is a best practice to use 74LS139, because this contains the exact number of peripherals that you can connect to, whereas this 74LS138, if you use this, you have a lot of this unused pin, so it'll be a waste of input and output. Okay, so that's the difference between full address decoder scheme and partial address decoder scheme. Again, full address decoder scheme, if we want to recap, you use a NAND gate for this. You use a NAND gate for this. Whereas for the partial address decoder, you either can use this intermediary 74LS139 or 74LS138. So that's how you design a partial address decoder. So let's look at finally okay, let's look at logic control for read and write memory. So if you remember right, apart from chip select, your memory have a pin which denote by read and write. Okay, read and write. So again, this is not very, this is not very important, but then just you need to know it as well. How does how does the 68K tells the memory whether you want to read the data from the memory or you want to write something into the memory. So how are you going to do that? Basically, the circuit look like this. Okay, consists of 4 NAND gates. Okay, 3 inputs. So if you figure out what's the output of the NAND gate over here, it will be like this. So you have 3 inputs, 1, 2, 3, UDS, LDS. Remember back, your UDS, LDS is connected to the first address pin A0, which denote UDS and LDS. So you have UDS and LDS, then you have read and write pin that is connected to the 68K. So based on these 3 condition, 3 pin over here, you can tell the chip what you need to do, whether you need to write. So write meaning is denoted by this WR. Okay, write at the upper word, or write at the lower word. Okay, or read at the lower part of the data bus, or read from the upper part of the data bus. So you can see here the lower and the upper is denoted by this here, this column over here. So for example, if it's 001, then you are telling the memory to write and at the upper part of the memory. So the upper part is D8 to D15. So this part will be valid and this part will be invalid. If it's on the lower side of the memory, okay, the even and odd, okay, you can imagine this even and odd, the lower side of memory. So when it's 1, UDS is 1, LDS is 0, then you are telling the memory chip to write at the lower part of the memory. So the upper data bus will be invalid and the lower data bus will be valid. Okay, so you can just figure it out from this truth table. So there's nothing fancy over here. So it's just how you're going to logic control for read and write memory process is performed in 68K. So I think that's all for today. Okay, before that, please have a look at this tutorial part. Sorry, this tutorial part. Okay, there's 3 questions over here. Okay, now make sure you do the tutorial, because I guarantee you that memory section will be appear in your final exam. So there is a question on designing a memory system in your final exam. So make sure you do this tutorial. So there's 3 questions. I think it's not very hard, and I hope you do it. So that's all for me. If you have any question, you can always ask me via Microsoft Teams, or message me. So until then, I'll see you next time.